Hello, my name is Krsna, and this video demonstrates the complete workflow and mechanics of my custom K-nearest neighbors pipeline. Step 0 begins with an initial exploratory data analysis to understand the row shape of our census data. By examining the demographic bar charts, we immediately identify a severe class imbalance, which is specifically the overwhelming majority of individuals that fall into the lower income bracket. We also review the numerical statistics, which reveal massive differences in scale between features like age and capital gain. Identifying these two major issues right at the start dictates our entire approach, establishing exactly why we must apply normalization and use dynamic evaluation metrics later in the pipeline. Step 1 is the first formal analysis of the dataset. This step addresses key components of our dataset within the pipeline, such as dropping incomplete vectors with unknown values and removing the final weight variable, as this is not relevant to our model and is irrelevant census data. This returns us with 30,162 instances. Moving on to step 2, we normalize and transform our data. As K-nearest neighbors requires numerical features only, we apply one-hot encoding to translate the categorical features and expand our dataset into a total of 95 predictive dimensions. We also apply min-max normalization to the data to constrain our features. This prevents larger integers, such as the capital gain, from artificially skewing the Euclidean geometry. Step 2.1 allows us to confirm the dimensions and displays the first 5 rows to confirm that the data is transformed correctly. In step 3, we apply an 80-20 data split for training and testing, which is to address dimensionality mismatch and scaling data leakage, which is further explained in the report. We use a fixed random seed of 42 for this to ensure that our results can be recreated and reproduced. This leaves us with 24,130 training instances and 6,032 testing instances. We then move to our K-nearest neighbors predictive engine, which works by calculating the Euclidean distance between a test instance and all training instances. It then isolates the nearest neighbors and determines the final prediction using a simple majority vote. We now run the hyperparameter tuning loop and the initial K-nearest neighbors model, which evaluates our dataset across a spectrum of odd K values ranging from 1 to 15. To avoid a severe computational bottleneck of over 1.1 billion calculations, we architecturally optimized this step through revisions to our code using array slicing. We calculate the distance matrix only once, extract the top 15 neighbors, and simultaneously evaluate all K values. This reveals our baseline optimal model is K equals 9. Step 6 moves into advanced evaluation. We generate receiver operating characteristic curves from scratch to prove that higher K values actually calculate better probabilities. By moving away from the strict 50% majority vote, we dynamically hunt for the specific probability threshold that maximizes our F1 score for each individual K value. In step 7, we generate a comparative multi-metric grid. This visually illustrates the mechanical trade-off between precision and recall and proves how our dynamically optimized thresholds consistently outperform the baseline model significantly in recall and F1 score. Step 8 grounds these percentages into row numbers using side-by-side confusion matrices. By shifting the voting threshold to 0.38, our optimal K equals 13 model deliberately sacrifices a small margin of precision to force a massive spike in recall. As you can see, this successfully rescues nearly 200 high-income earners from being misclassified, successfully overcoming the majority class bias.